The other technique that we use to approximate our integration comes from the use of parabolas. So we divide the interval from A to B into subintervals of equal length. But this time you have to be sure that n is an even number. So you can see the first parabola right here. So it goes through P0, P1, P2. And then the next one picks up on P2 and goes P2, P3, P4. That's a little hard to see there, but there's the second parabola. And then the third one comes up like this. So you can look up the theorem and the integration, but I think I might pull that in on the next page. So it says that we have the form y equals ax squared plus bx plus c. So the area under the parabola, and you work forward and so forth, and then we find out down here that we have y sub o plus 4 y sub 1 plus y sub 2, and we can then the area under the parabola becomes this value right here. So shifting it horizontally, it doesn't change the area under it. So we can kind of look through, and the second parabola looks like this. So here's your Simpson's rule. We use h over 3, and here's our first parabola, and here's the second parabola, and so forth to the end. So what we have is we have h over 3 in each of them. Y sub o happens exactly once. And then notice the pattern, it's 1 and then 4 and then 1. So we have one of these, 4 y1s, 1 y2, and another y2, because the end of the first parabola is beginning in the second parabola. So we have 2 y2s, 4 y3. Here we end with y4, and the next parabola starts with y4, so we end up with 2 y4s. And so forth accordingly, and again, the one that happens once is the beginning and the end. So here you can see that the pattern of the coefficients are 1, 4, 2, 4, 2, 4, 2, 4, 2, accordingly, 4, and then 1. It's called Simpson's rule after the English mathematician Thomas Simpson. And here's your generalization. We have x over 3, and notice the coefficients 1, 4, 2, 4, 2, 4, 1. Let's go back. That's because this one happens once. It's only in this parabola. And because of the parabola and the area under the curve, that happens 4 times. This one happens once in this red parabola, and then it happens again in the gray parabola. So this one has a 4, it's the bottom of the parabola. And then this point happens in both parabolas, and this is the 4 because it's the vertex of the parabola. And then this happens once at the very end. So I'm going to bring Simpson's rule in. Here you can see Simpson's rule, and it's the pattern we just talked about where n is even, and delta x is b minus a divided by n. So let's go back to that parabola we talked about in the first half of this lesson. N equals 4, so we're following the rules. So remember our Simpson's rule says delta x over 3. That's the same thing as 1/3 delta x. So we're going to say area equals 1/3. And our change in x, is still a half, because delta x is still a half down here. And then we're going to use Simpson's rule. So it says we pick up this first y value once. The second one is the center of the parabola, so we multiply it by, it's the vertex of the parabola, so we multiply it by 4, 13 over 4. Now here's our first parabola right here. Do you see it? That's the first parabola. And then the second parabola is this one right here. There's only 2 parabolas because n equals 4. So this y value of 4 happens twice because it's the end of the red parabola and the beginning of the blue. So we say 2 times 4. Plus 4 for the center of the vertex of the parabola. So 4 times 21 over 4. Plus, now 7 is the end of the whole thing, so it only happens once. So the area is 1 over 6, because 1/3 times 1/2 is 6. And we have 3 plus 13 plus 8 plus 21 plus 7 when we multiply those crazy things out. So if we add up all those numbers, here we have 52. So we end up with 52 over 6, which reduces to 26 over 3. If you remember when we integrated this, we got 26 over 3. I think Simpson's rule is the best approximation. So that's the one I would recommend. 26 over 3. This is the 1 over x, where n equals 10. So using Simpson's rule, you can see that their change in x is 0.1 right here. And the y values accordingly. So this is what you get when you use Simpson's rule. And the real integral is 0.693147. So we're very close here, much closer than the trapezoid rule or the Simpson's rule. So to compute the error, you compute the error of the trapezoid rule and the Simpson's rule. And it's a weighted average of the both. But there is a formula for Simpson's rule. But take a minute and work through this example so you can see that it's true. So pause the video. Make sure you come up with this decimal for your Simpson's rule. And here's your formula for the error to find Simpson's rule. As we talked about at the beginning of the lesson, sometimes there's not an equation and you need the area under the curve. So look at this problem. It says this figure shows data traffic on the link from the U.S. to Switch, the Swiss Academic and Research Network, on February 10th, 1998. The data is a little bit old. D of T is the data throughput measured in megabits per second. Use Simpson's rule to estimate the total amount of data transmitted on the link from midnight to noon that day. So we need to find the area under the curve because dt is the data throughput and it's measured in seconds. So we need to find it accordingly. So the first thing we do is read the chart and create an XY table, or you could plot it and work through it that way. So as we get ready to find the area under the curve, notice it's measured here in megabits per second, and this is in hours, so it needs to be changed to seconds first. 0 seconds is still 0 hours. I'm sorry, 0 corresponds. 3 hours is a lot of seconds. So they took the data that was given to them and they gave us a table. So here we see the total amount of data transmitted by noon is this number. And they gave us, here at the bottom of the screen, you can see that they gave us this table where here we have hours, which are not important. We need seconds. So we have seconds, and then we have the amount of data transferred. So Simpson's rule says we start with our change in x. And our change in x is 3,600 because it's 3,600 seconds every hour. And we divide it by 3 because remember Simpson's rule starts with delta x over 3. And then we have 1 of the dt's and 4 of these and 2 and 4 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 and 1. By the way, if it doesn't end up 4 and 1, then you made a mistake. So, just so you know, be careful about that. So our delta x is going to be 3,600 because that's our change in x over 3. So then we have change in x over 3, and this is what the equation looks like down here. So it comes out to be 143,880. But this is a very actual application for why we would need something like Simpson's rule or trapezoid rule or midpoint rule. So the concept's not too very hard. You've got this. Thank you.